Thank you. Yes, it's
Okay, I'm going to stand here under the microphone so everybody online can hear me. I'd like to thank everybody for being here today, both in person and online, for the master's thesis defense of Aditi Tripathy. I just want to run through a few logistics before I introduce Aditi, and then she can introduce her work. So this is a public defense. Aditi will talk for about 45 minutes. At that point, we'll open the floor up for questions. In the room, you can just raise your hand. Online, you can either chat in your question, which might be easiest, and I will monitor the chat so Aditi doesn't have to afterwards, and I can ask her the question so everybody in the room can hear also. And then at the hour point, we'll ask the public to dismiss themselves. Committee will deliberate and talk with Aditi, and then hopefully this will all be over by noon today, and we'll be moving to a celebratory lunch. So with that, it is my great pleasure to introduce Aditi Tripathy. She came to UNH directly from URI. She actually studied at URI under my PhD advisor, so it's kind of full circle now to have Aditi coming through here and defending her master's today. Aditi is continuing a tradition that's been developing here at CCOM and definitely within my lab and within Tony's lab of students getting jobs, having start dates before they've defended, which is a testament to the quality of students and especially of Aditi in her work and in her passion for research, that she has a job ready to go to. That's usually, step one of career success. So you've already taken that step. She'll be going to Tetra Tech in the Boston area by the end of this month. And so I always feel it's necessary to tell you a little story or, about people who are defending when I introduce them. So this one really illustrates commitment to the field of science, especially oceanography. So Aditi came to us without ever having gone to sea offshore for any extended period of time before. So she was able to go to sea with us about 6 months ago or so. We went on a boat and we got absolutely zero science done, first time in my career, because the weather was so horrible and she was so sick and not feeling well, and little fear was there, but she came back and she said she'd do it again. And so I really, so I admire the tenacity there, even in the face of adversity, and know that that is definitely a quality that shows her commitment to science and to oceanography. So with that, I will let Aditi talk about the impact of hurricanes on the acoustic detection of cetaceans, and she will be introducing her committee. So thank you for being here.
Thank you, Jen, for the introduction. And thank you everyone for coming here to support me and everyone on Zoom for attending. I really appreciate it. My thesis focused on the impact of hurricanes on the acoustic detection of cetaceans. But before moving forward with that, I'd like to introduce my committee to you. My advisors, Jen Mixes-Olds and Tony Lyons, and my committee members, Tom Littman and Kim Lowell. Thank you so much for all of your input and advice and guidance and whimsy throughout all aspects of this project. I really appreciate it. So a brief overview of and setting up the stage for what I did. Passive acoustic monitoring, or PAM, is valuable for understanding the behavior, distribution, and abundance of marine mammals. It's particularly valuable for species that are not easily observable using visual methods in areas that are not easily accessible throughout the year. And it's also an advantage over active acoustics because it's a non-invasive method. So what happens when multiple hurricanes pass over your receiver? Hurricanes are really loud. They increase the ambient sound at 40 hertz to 50 kilohertz, and this is because of wind wave interactions at the surface and oscillating bubbles due to rainfall and breaking waves. And we really care about this because even though hurricanes are short term, they can acoustically mask signals of interest from other sound sources. Here's a spectrogram of Hurricane Dorian and Humberto at the ADEON Blake Escarpment site. A spectrogram is essentially a heat map showing the sound intensity over time, and brighter colors indicate greater intensity. And as you can see, so time is in the x-axis over days, and y-axis is frequency in hertz and a log scale. At frequencies below 100 hertz, hurricane presence is obvious, but there are other sources of noise when the hurricane is not present. But above 100 hertz, hurricane are the dominant sound source, and that can impact detectability of sound sources that produce sound at those frequencies. So passive acoustic data were collected from the Atlantic Deepwater Ecosystem Observatory Network, or ADEON. The ADEON lander network is located in the southeast coast of the US along the outer continental shelf, and the landers range from Virginia Inner Canyon down to Lake Escarpment in Jacksonville, and the depths are from 200 meters down to 900 meters. And the yellow circles represent the standard lander setup, which is a passive acoustic hydrophone and physical chemical sensors that measure CTD and oxygen. And the green circles represent the standard setup with active AZFPs. 3 powerful hurricanes were captured during the data collection period: Hurricane Florence, which is category 4, Hurricane Dorian, which was category 5, and Hurricane Humberto, which was category 3. But as you can see, the colors are different along the trajectory, and that is because hurricanes speed up and slow down as they move forward in their trajectory. That is because of changes in translational speed. So the intensity is different at each site. So the minimum category was 1 at the lander sites, and maximum was 3. At some sites, hurricane presence was not observed. So that brings me to what I set out to do, was to understand the impact of hurricanes on cetacean probability of detection. And to do that, the first objective was to assess changes in ambient sound due to hurricanes. Previous studies have shown that ambient sound increases due to hurricane presence, but the frequency level impacts have not been closely studied, which is, this study is the first to do so. And within those frequency bands, the impact on signal detection has not also been assessed. So that is the second objective, to assess the impact of changes in ambient sound on detection of cetaceans. So before doing all of this, I'd like to bring your attention to the passive sonar equation. We use the broadband sonar equation because noise is broadband in nature, and the signals of interest were modeled to be broadband in the study. Sonar equation is essentially an energy balance sheet. The source level, we can pretend it's like sperm whale here. Source level is the acoustic energy radiated from the sound source. The propagation loss, PL, is the measure of how much the energy degrades as the sound propagates away from the source. The noise level is the noise of the receiver that is capturing the energy from the source. And array gain and detection threshold are properties of the receiver. And our term here is range. Z array, or Z array, is the depth of the array, and Z target is the depth of the target or the cetacean source that we are interested in detecting. And that gives us the signal excess, which is essentially how much the signal to noise ratio needs to exceed the detection threshold that we set in order for us to say, yes, the target is present, or no, the target is absent. So the first term I'd like us to focus on is the noise level term. To do that, before analyzing any of the sound, it was very important to carefully quantify the duration of hurricane presence at each of the lander sites. I struggled with this a lot in trying to figure out how to do it, because most studies would use changes in sound to indicate that the hurricane was there. And that wasn't helpful to me. So we did that by using the non-parametric change point analysis, which detects changes in a time series based on a chosen statistic. In this study and in this example, it was changes in mean. So an example here is discoveries per year from 1860 to 1960. And whenever the mean changes, there's this change point or structural break that's detected in the time series. So this method was applied using the guidelines from WMO for defining extreme weather events on the hourly wind speed time series local to each ADEON site. And that gives us the before, during, and after periods to analyze the sound. So from the change point detection, and the vertical bars here are the change points. We have the during period of Hurricane Florence at Wilmington and Hurricanes Dorian and Humberto at Blake Escarpment. As you can see from the dip in the wind speed here, that the eye of the hurricane was directly above the receiver, which is really cool to me. And a thing to note, though, is when there's a single hurricane in the time series, it was easy to define the before and after because the length of the during period was consistent. But for overlapping hurricanes, such as at Blake Escarpment, the intermediate period was halved, and the length of those individual periods were used to define the before and after of the successive hurricanes. So now we have the before, during, and after. It's time to analyze the sound. The analysis bands range from 10 hertz all the way to 7 kilohertz. That includes the frequencies of hurricane-induced wind and the cetacean sources that we focused on. And the temporal and frequency resolutions were 1 minute and decadecade, which is 1/3 of an octave. That is the minimum recommended resolution for ambient sound analysis. And 6-hourly statistics of sound level were assessed at 10th, 50th, and 90th percentiles, which is the quietest, intermediate, and loudest ocean sound conditions. 6 hours was chosen because we needed a large number of samples for the statistics because hurricanes are very short term, but also it was to be consistent with the state change reporting by the National Hurricane Center. And analyzing the sound gives us the noise level term in our sonar equation. Here are some examples of the sound level changing during hurricane presence. Once again, the vertical bars denote the change points showing the during period. This is at Blake Escarpment. The purple line is the wind speed, and the 3 lines here are the ambient sound level at the 10th, 90th, 10th, 50th, and 90th percentiles. They are denoted here in exceedance levels. L90 is the 10th percentile, L50 is the 50th percentile, L10 is the 90th percentile. As you can see, 10 to 100 hertz, there is some change, but not really. But in the 100 to 1,000 hertz, sound level increased a lot during hurricane presence, and then it went back down again, and then went back up again during the second hurricane. Same in the 1 to 4 kilohertz and 4 to 7 kilohertz bands, hurricane increased the ambient sound level during its presence. And this was expected as previous studies have shown that hurricane impact is greater at frequencies greater than 100 hertz. But now that we have the sound levels and we know that they change, it was time to estimate the probability of detection within those frequency bands and within those percentiles. We have 3 whales, 3 hurricanes, 6 sites and 3 percentiles, and only 1 grad student. So it was really important to pare it down because, of course, the real reason is if the noise level is not statistically different during hurricane presence, the probability of detection due to noise cannot change. So I have a couple tables showing here which of the sound levels made it to the next objective and which were left behind. A way to understand it would be fin whale ambient sound level did not significantly change during hurricane presence at Charleston Bump, which means probability of detection was not estimated for that whale at that site. Similarly, for Hurricane Dorian, it was mostly the lower frequencies that were left behind, so fin whale PD was not estimated. And then usually at the 90th percentile, which is the loudest ocean conditions, sound level did not significantly change. So the black squares indicate the excluded sound levels, and the colored sound levels were passed on to the next objective. Similarly for Hurricane Dorian. And that brings us to the source level term in our sonar equation. Sources are the sound sources we are interested in detecting. The first source is fin whale. It was the low frequency cetacean in this study. Fin whales, the target vocalization that we focused on was the 30 to 15 hertz downsweep, or also known as 20 hertz pulse. It is known to be a song component produced by males for attracting females. And the source level was 181.9 plus or minus 5.2 dB, assumed from Stimpert et al. The mid-frequency cetacean in this study was minke whale. The target vocalization was 50 to 300 hertz pulses. constant pulse type was used in the study because it's the most well documented. Of course, the function of the pulses are not currently known, but they are assumed to be for reproductive purposes and a song component. The source level was 168.9 plus or minus 6.6 dB, assumed from Risch et al. And the mid to high frequency cetacean in the study was pilot whale. There are two kinds, short fin pilot whale and long fin pilot whale. The target vocalization was whistles. Whistles are a communication type call used for keeping in touch when they're not foraging over long distances. Because the fundamental frequencies of the two types of whales overlapped, the two species were pooled together, and the source level, which is the only source level available for this type of whale, was assumed from Koch et al. It's 146.5 plus or minus 9.5 dB. So now the array gain, which was assumed as 0 in this study because it was a single hydrophone, that's the property of the receiver. Detection threshold was assumed to be 0 as well. In the real world, though, detection thresholds depends on the research objective and the sound source that needs to be detected. There is a trade-off. If you have a high detection threshold, you have a low false alarm, but if you have a low detection threshold, you can have higher probability of false alarm. But to keep things simple, we assume the detection threshold was 0 in this study. So now the only term left is the propagation loss, which is the measure of how much the acoustic energy degrades as sound propagates away from the source. And that was modeled using the Monterey-Miami parabolic equation model, or MMPE. The 2D version was used in this study. The inputs were cetacean source frequency and depth. Water column sound speed was collected from ADEON. Range-dependent bathymetry was from JEPCO, and range-dependent bottom properties were from the NOAA DEC 41 surficial database. Here's an example of propagation loss for fin whale, assuming the source is at 15 meters. You can see the acoustic energy is propagating all the way up to 100 kilometers in range. Of course, the ranges were modeled differently for each cetacean. It was 100 kilometers for fin whales, 20 kilometers for minke whales, and 5 kilometers for pilot whales. Another thing to point out is 1 kilohertz whistles were used for pilot whales, even though the fundamental frequency upper limit is 11 kilohertz. This was done because from initial propagation modeling, it was found that all whistles past 1 kilohertz would propagate away in a surface duct, so they would not reach the receiver at the bottom. So modeling with all of these inputs, I modeled propagation 168 times. It gives me propagation loss at the depth of my receiver at each site for the center frequencies of the cetaceans, which are the representative frequencies, in 4 cardinal directions. 4 directions were used in the study to highlight the differences in directionality, but ideally you would want to model it along 360 degrees to have a comprehensive view of propagation loss. So here's an example showing propagation loss at Hatteras South in different directions. The sound speed in these directions is the same, obviously, but the bathymetry is very different along the different directions, and so are the sediment types. The vertical bars here denote the change in sediment type, and the white line is the bathymetry. And in the east and south directions, from the minke whale source, the acoustic energy only goes up to 10 kilometers. But in 2019, where the sound speed is a little different, the propagation is great. The sound energy from a minke whale source goes all the way up to 20 kilometers. So if our receiver is anywhere, which is at 294 meters, along this horizontal distance, it can capture the energy. So now we have all of our terms, and that gives us a signal excess. We have our assumptions about the source level from the literature, the propagation loss, which was modeled, noise level, which was measured, array gain and detection threshold, which were predetermined. And every term in the sonar equation is in dB, and that needed to be linearized to then give us the R array term in the probability of detection equation. That is the signal to noise ratio in linear form that is exceeded to make a detection. And probability of false alarm was assumed to be 10 to the minus 12 because we wanted a 99% probability of detecting and a very, very low, almost 0% probability of false alarm. And M here is the number of independent samples that can be calculated from the sampling frequency and the sampling duration of the instrument. Putting all of this together, the source level, propagation loss, noise level, and the detection parameters, and all of the different components that go into it, these terms were put into a Monte Carlo framework, and it was iterated 10,000 times to limit the amount of Monte Carlo errors. And the broadband passive sonar equation and the PD equation were used to then estimate mean PD along different ranges for different cetaceans. So essentially there was a value of probability of detection at each range step for each of the whales. And using that, we were able to estimate the detection range, which is really the limiting distance. It is where PD is at least 50%. So past that range, you cannot reliably detect cetaceans. And along the 4 points, that gives us what I refer to as the detection area in the study. So the colors in red indicates before, green is during, and blue is after. And the 4 points are, so the contraction and expansion of this figure is because of the noise level, but the shape is determined by the range-dependent propagation conditions. As you can see, the detection area decreased during hurricane presence for a minke whale. Similarly, for a pilot whale, detection area decreased as well, and it was actually down to 0 during hurricane presence. This is noise level at the 10th percentile. And at the 50th percentile, detection area decreased once again. And after the hurricane, it almost reverted back to pre-hurricane conditions. Similarly, at the 90th percentile, detection area decreased, although you can see for the fin whale, for the minke whale, it's not as drastic as at the 10th and 50th percentiles, which shows the variability in the sound level using percentiles. But for fin whales, which were vocalizing below 100 hertz, I had not expected many changes in probability of detection because hurricanes impact frequencies greater than 100 hertz. But interestingly, the detection area increased during hurricane presence. And similarly, at the 90th percentile, detection area increased as well. And this might be because of suspension of commercial shipping activities during hurricane presence. And also if the fin whales or low frequency vocalizing cetaceans left the area, it might be because of changes in prey distribution or changes in communication space that may have led them to do that. So that was an interesting finding. And that brings us then to summarize the results from the PD. Here's an example of changes in PD for cetaceans at Charleston Bump. The colors here indicate changes relative to the before period. PD always changed during hurricane presence, but whether or not it increased or decreased was dependent on percentile and the frequency band. And after the hurricane had passed, in some cases, detectability reverted back to pre-hurricane conditions, but in most others, it either increased or decreased further from pre-hurricane conditions. And to conclude, hurricanes increase ambient sound at frequencies greater than 100 hertz. Sound level increased at the lander sites up to 25 dB in the 1.1 to 7 kilohertz bands, and it decreased at several sites in the 10 to 100 hertz band, which we expected. PD had site-specific, cetacean-specific, and hurricane-specific changes, and that going back to this plot, this table, we can see how different those changes are. So it's really difficult to have a direct comparison along different directions and different sites and different intensity hurricanes. Detection area generally decreased during hurricane presence for minke and pilot whales, but detection area also decreased for fin whales for certain hurricanes, but increased during Hurricane Humberto, which was a relatively fast-moving hurricane. Changes in PD may impact passive acoustic measurements and the interpretation of those measurements. And this is relevant for Navy in their testing ranges, commercial shipping operations, oil companies, offshore wind farm development, and the changes need to be accounted to decrease risk of acoustic impact on cetaceans, to improve performance of sonar monitoring systems, and to improve mitigation measures, as activating mitigation can be costly if there's a false alarm. This also can result in changes in communication space if detectability increases or decreases. Particularly if it decreases, it's possible that cetacean species might not receive enough information about potential mates, which can have individual or population level impacts and decrease mating opportunities. None of the species in this study were really endangered, but this could be important for species such as the North Atlantic right whale, which are a couple hundred in number. So every individual matters, and changes in mating opportunities can really impact their population. But more importantly, the direct impact of the study is changes in density estimation of cetaceans in a given area. Density can be estimated using this equation. D is the density estimate, N is the number of calls, A is the area surveyed, C is the false alarm proportion, P is the probability of detection, which we estimated, R is the call rate of the cetacean, and T is the time spent monitoring. So in a little exercise, if we assume 10 fin whales are calling for 15 hours a day, fin whales can call for up to 32 hours. We have this many number of calls detected, the area surveyed, modeled up to 100 kilometers squared. The false alarm proportion we can assume to be 0. And the average probability of detection was 45% at one of our sites. And call production rate was assumed as 45 calls per hour from Stimpert et al. And the time spent monitoring was 6 days. So putting all of this together, we get a density estimate of 0.011 whales per 100 kilometers square. But obviously, as we saw during hurricane presence, PD changes. So accounting for that difference, we would have changes in the number of calls detected before, during, and after hurricane presence. The area surveyed, which was shown from the detection area, changes during hurricanes. It decreased to 30 kilometers squared from the example. False alarm proportion is the same. And then PD changes from 45% to 29% during hurricane presence. Call production rate is the same, and time spent monitoring was 6 days in this example, but every site, the time spent before, during, after was different. So with these assumptions and accounting for the changes, the density estimate before was what we had before in the example, but during the hurricane, the density could be overestimated for fin whales. And after, it reverted back to almost the same as before. And that shows the value in accounting for the changes in detectability, because without it, there could be a risk of overestimating or underestimating depending on the changes. And of course, probability of detection isn't the only term that was impacted by changes in detectability. The number of calls detected and the area also change. Another thing I didn't mention is the hats here indicate the variability, as these are estimates. So changes in detectability can have variability in the individual parameters of the density estimation, as well as the overall estimate itself. So with that, I would like to thank our sponsors, and I would like to thank Ernst Linder and Jamie Pringle, Lucas and Jesse, and some friends from CCOM. Thank you so much for all of your support and love and hearing me complain about various things throughout the 3 years I've been here. I'd like to thank my dog Dexter for being a very good boy, and happy to take any questions.
Katie, when you talk about your propagation loss, and you're talking about the soundscape profile, during a hurricane, I typically would expect there to be a lot of mixing in the surface, and it looks like you're using soundscape profiles that are from when you can go out on a ship. Do you account for that mixing and how that might change the shape of your profile of your models? And, but yeah, do you? And if you didn't, like, how would you expect it to change your results?
That is a very great question, and that's a component that I was really interested in exploring. The soundscape profile. Ideally, I would have liked to use a before, during, and after, but we didn't measure the sound speed during those times because the data was opportunistic. But I would expect it to change before, during, and after, and that would give a more accurate estimate of probability.
Just to add to that, like when in the hurricanes, would that like not be a well mixed layer? So would there still be density stratification that would change the speed of the sound during hurricanes?
It depends. All of our receivers were at the bottom. So in other studies, I've seen like there is changes in sound speed during hurricane presence, but it doesn't change the structure of the stratification or anything enough to have changes that would then lead into probability of detection.
Good job. You mentioned that it would be like this information is kind of useful for industry and maybe the Navy with detections during versus outside of hurricanes. And I was sort of wondering, are a lot of those industries or the Navy kind of suspending operation during hurricanes? Like, would you expect them to still need to detect those animals and like worry about interfering with them, or is their behavior kind of reduced that would impact the animals?
Can you expand on that
Yeah.
question?
So I guess like, all right, you have like a big hurricane coming. Like you said that wind farms would be interested in how well they're able to detect the whales during versus not during a hurricane. But you expect wind farms to not really be operating as much during a hurricane, right? So like, I guess to what extent are a lot of those industries continuing to operate during a hurricane that detecting them is still valuable?
That's a really good question. Really good question. I would imagine it would be more important after the hurricane has passed because many slides back, but the table, yeah. So after the hurricane, it seems like there's still a lingering effect. So the detectability is different from before. So it would be important for people monitoring to account for that difference because it's not the same as their estimate for resuming construction.
Do you know how long after the hurricane does the probability return to like previous pre-hurricane conditions?
It depends. So I used from the change point analysis, I had like fixed after periods, but obviously the after is any point of time after the hurricane. So within those 6 days, for example, probability of detection did not revert to pre-hurricane.
I had a quick question about slide 24. So you showed skewed area in which detection was happening.
Yep.
So would the reason be, and you mentioned this recently, the ship movement in the area, but like would there be ship movements during hurricanes?
So for the fin whale case, because the dominant sound sources are broadband shipping and low frequency vocalizing species like fin whales, I would not expect hurricanes to impact changes in detectability here. So here in this example, it would be that shipping was paused during hurricane presence. And that's why detectability increased. Whoever wants to go first.
Can you go first?
First of all, great job.
Thank you.
I don't know too much about whales, but for the, I believe, fin and minke whale, the frequency that you used was based off of their mating calls, right? They have a mating season like other land animals, and if they do, does that line up with hurricane season?
I didn't look into it for fin and minke whales, but for North Atlantic right whale, the mating season starts in November, and all of these hurricanes were in September. So it really depends on like if they're trying to sing songs during the hurricane season, that might then kind of lead into November where they don't have enough whales responding. People should not respond. So it's possible.
Okay. In other studies, is the mating song the primary form of detection?
No, that would be a natural extension of the study to include other types of calls. I chose song type calls because they are very repetitive in nature and very frequently produced. And in the study site, that is what they would be doing. But there are several studies estimating detectability for echolocation clicks and other types of fin whale calls. They have very high frequency calls that are used for foraging.
So building on Jenna's general question of the source level terms, you had a single source level term for the specific type of call that you were trying to detect. And those had some pretty big bounds in terms of their sort of decibel level. And I guess I was just wondering if you could comment on whether or not that was implemented in the study, if you considered sort of those bounds in the study, and then also those calls would be very specific in some cases to a certain sex of whale or maybe an age of whale as well. I imagine that mating calls are not made by baby whales. I actually know. And so I was just wondering if you could comment on whether, what population you're detecting and how things could be perhaps improved to consider the full population, especially for whales that might be endangered. You might care about, how many calves are born or mothers, as opposed to the maple whales that are trying to find food.
Yeah, so the entire source level.
All right, I'm trying to get to the slide where.
Oh, there we are.
Sucks.
So the entire distribution was used. I created a normal distribution, and that the Monte Carlo framework basically sampled different source levels to count for all the variability. Of course, source level estimation is still a topic of study because it involves tagging whales. Like for this pilot whale, for instance, it was just 2 pilot whales that were tagged. And this is the only source level available. I think most studies I've read or remember at this point, they were all adults. So it would be good to use call types for different sexes and different ages, and especially like mother-calf pairs, which for right whales, again, they prefer not to be detected when they're with their baby. So that would be important. If detectability increases, that might increase risk of predation.
Okay, we got 2 questions online. First is from Kevin Durham. Excellent presentation. Sorry if I missed this, but what were the assumptions made about the depth of the whales when vocalizing and how this fits into the propagation loss models? Those PL plots were mesmerizing. And let me just get to the slide, I think.
I've never heard that word to describe propagation models. I appreciate it.
Here you go. There's that information.
Yeah, so the source depths were assumed from the literature. Fin whales was from Stimpert et al., minkies was from Risch et al., and pilot whales was from Koch et al. And that is, so there's a source input file that you run each time with different environmental properties, and depth is one of the inputs that you have in that file. So obviously, if the depth changes, the propagation loss would change.
Question.
I was just wondering, you showed the 2 propagation losses where for one of the whale types, I forget if it was the minke, you basically had complete loss after however many kilometers, 8 kilometers. And then you had another situation, I think the next slide probably, where you have significantly better propagation. Why is that? What in the sound speed profile has changed here between the previous sound speed profile and this one? What is it that is making that propagation so much greater?
Temperature and salinity.
I mean, yes.
Yes.
Is it because the hurricane has come through and homogenized the upper water column, or is it something to do with the deeper water?
This is not to do with the hurricane because the sound speed profile from the previous slide was from 2018, and this was a year after. So it would be general changes in the sound speed profile, not due to the hurricane. But this is the point where the sediment type also changes, so it would be an interaction of both.
So you're expecting the sediment type to change over the course of the year?
Not, sediments did not change,
Okay.
but
I don't think so.
the entire interaction with the sediment and the soundscape profile would result in these changes.
There's another question from Michelle Fournet. Many whale species adapt their calling behavior, including source levels, in response to ambient noise. How do you think the behavior of the animals, like the Lombard effect, where whales increase source level in response to noise, may change your results? So how do you think the behavior of the animals may change your results?
If the source level increases, that would make the whales more detectable. So maybe the noise increasing would not really matter as much as it did in this study, especially again for pilot whales, the source level is much lower. It's 146 dB. For fin whales, it's 182 dB. So if there was compensation due to the noise, maybe detectability would have minimal changes.
Lots of kudos from the chat, so you can read that later from lots of different people. Both people who asked questions online said thank you. You answered their questions. Any other questions? Oh, go ahead, Tony.
Slide 34.
Slide 34.
This is a thought question. I don't have the answer. Or I have an idea what I would do. But yeah, so when the detection probability increased and the ranges increased, you suggested it's due to shipping. So how can you unambiguously, or how do you think you could unambiguously say that that's true or not? That there are less ships during a hurricane. I mean, I would guess that's true, but because I know I would not be wrong. But,
Yeah, we would not want to go out in that weather.
but is there a way that you could say for sure, or closer to certain, if that's true?
That would be by looking at AIS data and tracking the ships relative to the hurricane. It's conjecture, but it's possible the ships are there and the propagation conditions have changed. So at this site, we can't really hear the sound from ships. Does that answer?
That's an answer. It's probably the best one. I'm just.
Any other questions from online or in the room? Oh, there's one.
This is really dense, but can you just describe like what is going on? Like what is the axis? Is that distance that the sound is propagating?
Yes.
From the center point.
So assuming the center point is where my receiver is, the calls from the whales, if the whale is facing this way, can be detected up to 10 kilometers during the hurricane.
Thank you.
We're calculating based on the propagation loss, like charts that you had before.
Yeah, based on the entire, so I had a PD value at each range step. So I basically limited it at PD's 50% here. So at any point in these areas, you can reliably detect the whale. And Nick was very helpful with that, actually.
There are two more, one comment really and one question online. Perhaps AIS data could be used to track changes in shipping, which is what you said, right?
Yep.
Okay, good. And then as an outsider to the field, I'm curious to know how you see the global climate change impacting your studies in the future, or maybe how they may be helpful to us facing it.
That's a really great question, and hi, Piotr. So this study really provides a motivation to continue studying episodic events. They have not been previously deemed as important because they're very short term, and then things do tend to go back to the way they were. Particularly in the North Atlantic, though, hurricanes are increasing in incidence. The Atlantic storm seasons have been like 21 named storms in 2020, and that is something that we should look into. And the increase in incidence of hurricanes is to do with the warming of the ocean. And as well as warm core rings, which are another episodic event, which are increasing in incidence in the North Atlantic. And that could have other impacts on propagation, for example, because they don't make noise, which should be studied.
I think we've come to the end of our question and answer period. Please join me in a wild round of applause for Aditi. So at this point, let's take it like a 5-minute break so we can transition to the committee. Tom, you should have been sent a Zoom to go into that's separate from this Zoom for committee discussion. So if you can do that now, that would be great. Aditi, lots of kudos coming in.
Hey, I'll look for it. Thanks.
Okay, great.